Well. Hey, welcome back to another Toolbox Tech Talk. This is take 2 of today's Tech Talk. Oh my God, take 1 went well for about the first 5 minutes and then the stream stopped. I just don't know what happened then, but maybe I'll pick up those viewers again if they get a notification, but otherwise they'll be watching the recording. Technical issues, they're always a drama. Well, yeah, today we're going to be focusing on Amendment 1 of ASNZS 5139. It was published a couple of weeks ago, and it's mostly a tidy up of some of the ambiguity in the original first edition of ASNZS 5139, the battery standard. Then today I'm going to be focusing on 2 main things. One is how to calculate the battery system fault current, which is one of the major changes. And the other is a little bit about room requirements and location. I think today's going to be a pretty short Toolbox Tech Talk. It is the last for the year, and I will be back next year, don't worry, with lots more content. So let's get into it. So first up is in red is the bits that are being deleted from the current version of 5139. So for clause 3233, we are removing that little bit on the end there that says short circuit current, and we're also removing the bracketed term prospective short circuit current, because we're referring to the prospective fault current at the battery terminals of the battery system. And how do we find out what those are? Well, there's a formula which is also being deleted because it now is an appendix and it's got a little bit more to it. So it says, instead of putting the formula straight into the body of the standard, it jumps you down to Appendix I. So Appendix I is new. So let's check out Appendix I. See if I can change slides. There we go. So this is Appendix I, which, wow, surprise, surprise, it looks almost exactly like the formulas that were in the previous deleted section, but with the little addition of a note at the bottom. And the note is the internal resistance of a cell, lead acid type or similar, may be determined by the method shown in AS 2676.1 and point 2. Point 1 is for flooded cells and point 2 is for sealed cells. So that's really only applicable to lead acid, nickel iron and nickel cadmium cells. And the formula above is for calculating the cell short circuit current. It looks pretty simple. So ISC, I short circuit, is just the open circuit voltage of the cell divided by the internal resistance of the cell at full charge. Well, piece of cake, right? No, because when it comes to lithium-ion cells, it's much more difficult. And that's what we're going to be looking at today, is how a manufacturer would calculate that. Now, I should emphasize, even though this is an installation standard, some of these requirements are putting the emphasis and the impetus on the manufacturer to give you this information. Because it does say, if you cannot get this information, you shall not install the battery system, says that elsewhere in the standard. So you really, really need to know what the short circuit current or the fault current of the battery system is. So let's take the example of how we would do it, so using your very common 18650 cell. Now, these are slightly bigger than a AA, and you'll find them in lots of equipment, including electric vehicles. It's amazing how you can mass literally tens of thousands of these together to make a big battery. But let's start with one cell. That's the way you measure it, and then you can calculate based on the number and parallel what the fault current will be. So there's a bunch of methods for measuring internal resistance of a lithium-ion cell, and we're going to run through those methods here. It's like you can see from this picture, it does require a bit of a jig. You do need to ensure very, very, very low resistance contacts with the cell itself to make sure that you're not falsely measuring voltage. So the sense leads there, the voltage measurements leads are in what's known as a Kelvin mode. So I'll explain that a little bit later on. And you do need to apply a load for most of the tests. You can use an oscilloscope, which gives you the most accurate results, or a digital multimeter. So as you can see straight away, this is not something for you do on the site when you're installing a system. This is something the manufacturer would do in a lab to calculate the fault current. So method 1 is known as a DC pulse or DC internal resistance test. Now the concept is basically it's a very fast current step, very, very fast. We're talking microseconds to milliseconds. And we're going to measure the instantaneous voltage drop when that pulse is applied. And it does actually represent the real world behavior of a cell, such as if you drop a spanner across a battery, that's going to be a very big pulse and therefore a large fault current. So this is the method 1, and setting up this method, you need a load to measure. So you have a battery in circuit with a 1 amp load on that battery. So it's the battery on the left with a load, a resistive load. And so in fact, in this case, the R is actually the battery, I should say. R is the battery that we're measuring the resistance of, and the current source is on the left. So we've got a constant current of 1 amp. Now the current should be, for a pulse test, actually quite high. Typically around the, if a cell's rated for 1C, 1C would be what the pulse test would be. So quite a high current value. And it's best measured with an oscilloscope. And you could also include a current shunt in the circuit to ensure that you're actually very accurately measuring the current rather than just relying on your power supply's display. Okay, so we need to get the state of charge around about the 50% mark, and there's a reason for that, which I'll explain in a minute. And the system needs to be at rest. So if you're charging it up to 50% or discharging it down to 50% approximately, you need to let it rest so that the quiescent voltage is stable. Then you apply the pulse. Now for an 18650 cell, that could be somewhere in the sort of 5 to 20 amp range for 100 milliseconds. And you need to, at that point, measure the instantaneous voltage and current that occurs as the change goes from no current to the pulse current. So how do you then determine the internal resistance of the cell? Well, it's the voltage before the pulse is applied minus the voltage after the pulse is applied. So that's the change in voltage, basically, divided by the test current. And use voltage at around about the 1 to 10 millisecond step. So you're looking at, that's why an oscilloscope is pretty handy, because you can actually see the time base. And at that sort of 1 to 10 millisecond step change, see what the voltage is. Now, it says avoid slow polarization region. It's quite a technical thing, polarization, but what's known as slow polarization is the region that reflects the time-dependent electrochemical limitations that emerge after the instantaneous resistive response of a cell. Yeah, it's a bit of a mouthful, isn't it? So that's one of the reasons that you need to do it at a stable temperature at around a moderate state of charge, like 50%, and having rested the cell. So if you're doing this test repeatedly, you'll start to get into the polarization region. So you need to let it rest between each test if you're trying to repeat the test for consistency. So that's the pulse test, method 1. Method 2 is current interrupt. So you start with a steady current, this time instead of a pulse, and you measure the immediate voltage recovery when that current's removed. And it's sort of equivalent to the direct current internal resistance estimate. So let's see how we do this. We discharge at a constant current and then abruptly turn it off, so interrupt to 0 amps, and measure the instant voltage rise. So it's kind of like the opposite of the pulse test, really. It's a depulse, well, not even a pulse. So you've got a constant current, you turn it off, and measure the change in voltage between constant current and the moment you turn it off. Once again, speed is key, so measuring using something like an oscilloscope or something that can capture a very short time frame. And then that will give you the internal resistance of the cell. Method 3 is surprisingly using an AC current. Yeah, an AC current on a cell. And this is very common amongst commercial testers because it's very easy to do. And I've even put a table in there showing the differences between doing the DC pulse test and the AC internal resistance test. So you pass a small AC current, typically at around 1 kilohertz. So this time it's not a high current. And it's a very fast test and low stress on the cell itself because you're not passing high current through it. So it really is just the resistance equals the AC voltage divided by the AC current. Pretty simple. So what are the pros and cons or the differences when it comes to the fourth line down? What is it? What's best for? Well, best for fault current is actually the AC internal resistance test, whereas the DC pulse test is best for power capability and looking at the effects of aging. So there you go. This is probably the easiest test to do, and it is the best for calculating fault current. But you do need an AC source. So we're not talking 230 volts AC. We're talking a frequency generator that can generate a small current. So around about 1 kilohertz. There's a little diagram of it, and you will need an oscilloscope to be able to measure that offset voltage because it's an AC applied to a DC source, and so there'll be an offset, a DC offset. Yeah, it's quite complicated, isn't it? Method 3, pros and cons. It's quick, repeatable, it's gentle on the cells, and the AC internal resistance is approximately equivalent to the ohmic resistance of the cell. So that's why it's not perfect, but it's pretty good for real-world tests. It is rather frequency dependent, so if you're going to be repeating this test, you need to do it at the same test. And it may not match what's known as the load lag. So looking at the different load levels and how much the voltage changes, it won't show you that, but it will give you the internal resistance, which is kind of what we're after. Method 4 is if you haven't got an oscilloscope and just a digital multimeter. A very simple way is just to basically apply a known resistive load to the cell and measure the voltage drop in current. So there you go. So you're doing a change in voltage from no load to load and seeing what that change is, and using change in voltage divided by current will give you the internal resistance. So it's kind of quick and dirty test. So the key factors affecting these results is all of these need to be trimmed as much as possible to keep standardized. So for instance, the state of charge should be the same when repeating this test. The cell temperature should be the same. How much rest time you give if you're repeating the test. Very important is to minimize connection resistance. So hence the Kelvin method of measuring resistance, where you've got a separate voltage measuring across the cell, not using the source voltage. Like if you've got a power supply, it'll tell you what the voltage of the power supply is, but then there'll be voltage drop over the leads. And also the pulse magnitude and timing will affect the results. So let's look at a typical 18650 cell. These are nickel manganese cobalt, I'd say, because they got a 4.2 volt nominal. And these are, let's say, an energy cell with around about 30 milliohms of internal resistance. And we can calculate the prospective fault current by dividing the cell voltage, 4.2, by the internal resistance, 0.03 ohms, or 30 milliohms. And that's at a massive 140 amps out of that little 18650 cell, which is only slightly bigger than an AA cell. Wow. You can see why they can start fires in rubbish trucks. You know, those little vapes often have a small lithium cell, about half the size of one of these, and they can create quite a big spark and set fire to things. So there you go. So best practice is to use the DC pulse with an oscilloscope. Make sure you're using Kelvin voltage sensing, control the state of charge and temperature, and if you're really scientifically minded, document everything, your method and timing. There you go. So now you're a qualified cell tester. But if you're doing a lead acid battery or similar, which actually from that standard AS2676 part 1 or part 2, depending on whether it's a flooded or sealed cell, you're told to use the formula here because manufacturers of lead acid usually will provide you with the internal resistance as part of the data sheet of the product. So it's fairly easy, but if it doesn't, you can spend some days doing this test. Look how long it's going to take you. Prior to testing, fully charge the battery and let stand in open circuit for a period not less than 12 hours and not more than 24. Discharge at the 3-hour rate and hold momentarily. Then increase the current to the 30-minute rate and hold momentarily, and measure the overall terminal potential difference in volts. Wow. So this definitely is a long duration test. So, and it is the recommended test for a lead acid battery. There you go. Okay, now let's jump on to another change in the clause in the standard due to these amendments, which is some of the wording. So in clause 4.2.2.1 general, it's telling you suitable locations for the installation may include. Now, it's asking you to delete the current list and then replace it with this, which is almost the same, except they've added in B rooms meeting the requirements of 4.2.5. Now, you should notice that it says suitable locations for installation may, and may being a term meaning not mandatory but recommended. So there you go. It's kind of a soft enforcement. It's not a must do. But if you're complying with 4.2.5, I've highlighted some of the key features in 4.2.5, which is in the current standard. So BESSes that are installed within a room so that access to the BESS is not obstructed by the structure of the building, fixtures or fittings within the room. So the idea is you can actually get to it. It's not a kind of in a box that you can't access easily. So, you know, if it's in its own enclosure, of course, it needs to have readily available means of isolation for maintenance and repair, of course. You also need to consider that the room has been selected to minimise the likelihood of build-up of other materials around the BESS or infestation of insects or vermin. So that's going to be your call as an installer. Is it a suitable location? You know, if it's a fuel storage room or a hay barn, it may not be. If it's somewhere where there's obviously damage from rats and insects and termites, it may be not suitable. There you go. And then the next one is you need to provide sufficient clearance to provide safe handling and access for installation, removal and maintenance. That's pretty important. And lastly, the pre-assembled integrated BESS must have a minimum, I said must, but it doesn't say must. These are shells, I should say. Must and shells are kind of the same thing. A minimum unimpeded access on the working side of the system. That means the side where you would be making any connections. You might be exposed to any live terminals. And no less than 600 mils of clearance, or the clearance specified by the manufacturer, whichever is the greater. So minimum 600, but if the manufacturer says 900, then it's 900 or 1 meter, whatever. The manufacturer's recommendations must be applied. But where access panels allow access to 230 volt AC connections, the minimum clearance shall be 900 mils. So once you've got a 230 volt AC, you now have an extra requirement of 900 mils. And lastly, this is a clarification about the amount of clearance when you've got a BESS installed in a corridor, hallway or lobby. And there's just a small addition to the top statement is from the original standard. A pre-assembled integrated BESS installed in any corridor, hallway or lobby shall ensure sufficient clearance from the BESS for safe egress of no less than 1 metre, and then we have to add from the front and sides of the BESS. And then additionally, there's a diagram showing that extends around corners as well to a 45-degree angle. So it's another addition of another figure showing that curved sweep of 1 metre from the sides right around to 45 degrees angle if there is a corner adjacent. So yeah, those are the egress requirements. So there you go. And just a reminder that the draft standard 4509 Part 1 is finished public comment. It was right up to Christmas Day. So that now is going back to the committee, and the comments will be reviewed, and we'll make decisions on whether to accept or reject those public comments. Generally what happens is unless there are significant changes based on accepting any changes from the public comments, it'll just go to publication some months afterwards. But if there is significant changes, and this is a call of the project manager from Standards Australia, then it may have to go through another public comment round. That's quite unusual actually to have 2 public comment rounds, but it is possible. I'm pretty excited because 4509 Part 1, which is applicable for electrical installations for standalone power systems, it's getting a little bit dated, last published in 2009, and a lot's changed in terms of technology. So really excited to see that standard being updated. And there's some parts of it which, if they do pass through the public comment phase, I think you'll be very pleased, particularly when it comes to connecting generators to a standalone power system. So there you go. Well, that's all I have for you today, and apologies for the live being interrupted at the beginning of the show, and I have to restart it. There seemed to be a bit of a network issue there. But otherwise, I'll see you back next year, as they say. Same time on a Sunday, 1 p.m. Australian Eastern Daylight Savings Time, 3 p.m. New Zealand Daylight Saving Time. Thanks for watching. Check it.